This is the first ever image of a black hole, released by the Event Horizon Telescope collaboration on April 10th, 2019. It shows plasma orbiting the supermassive black hole at the center of the galaxy M87. The bright region shows where plasma is coming towards us, and since it's traveling near the speed of light, it appears brighter when coming towards us and dimmer when going away. This is called relativistic beaming. From the images, scientists can tell that the plasma is orbiting clockwise. It takes around 2 days for the plasma to complete one orbit. Here, we are looking at the black hole using electromagnetic waves with a wavelength of 1.3 millimeters, radio waves. This was the part of the spectrum used to make the image because it can show us the features close in to the event horizon, and it can pass through the accretion disk and interstellar dust to reach our telescopes. The supermassive black hole in M87 is very active, meaning it's constantly feeding on lots of matter from its glowing hot accretion disk. But it also has narrow collimated jets above and below it, here shown in blue, thought to be created by incredibly strong magnetic fields. The jets extend out at least 5,000 light years, and one of them appears to be pointing almost straight at us. Relativistic beaming is again the reason we can see the jet coming towards us in this Hubble Space Telescope image, but not the one going away. Since the jet is pointed almost straight at us, I'm thinking our perspective is almost perpendicular to the accretion disk. But let's have a look at what we would see if we were looking at different orientations. The warping of space-time around the black hole means we can see light even from parts of the accretion disk behind the black hole. They are lensed above and below the shadow region. Not gonna lie, this is so trippy I could stare at it for a long time. So the big question most people are going to be asking is, why is the image so fuzzy? The answer is because it's so tiny. Don't get me wrong, the black hole itself is huge, supermassive in fact. As measured from this picture, the black hole has a mass 6.5 billion times that of our sun. The actual size of its shadow is nearly the size of our solar system. But located 53.5 million light years away, its size from our perspective is only about 40 micro arcseconds. That's the angle it makes on the sky. To understand what that means, take the whole sky and divide it into 180 degrees. Then divide a degree into 60 arc minutes, and an arc minute into 60 arc seconds. Divide an arc second into 100, and into 100 again, and into 100 once more, and that is the size of the black hole shadow, only about 40 micro arc seconds. It puts us at the very limit of what we are technologically capable of seeing. In fact, to get this sort of resolution, due to the basic law of physics, the diffraction limit, we needed a telescope the size of the Earth. That being impractical, the scientists used 8 telescopes spread across the globe. They all simultaneously observed M87, and as the Earth rotated, that helped fill in the Earth-sized telescope that they were trying to simulate. But M87 was not the only black hole they looked at. They also observed the supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star. It's much closer at around 26,000 light years away, but also much smaller, with a mass only 4 million times that of our Sun. It's also less active, only periodically gobbling up matter, and it would have much more variation over time, with matter orbiting every 4 to 30 minutes. Perhaps for these reasons, the image of Sagittarius A star isn't as good. But it still shows the same black hole features, confirming beyond a shadow of a doubt that black holes do exist. The general theory of relativity, published over 100 years ago, is supported again, in spectacular fashion, in the strongest gravities and at the limits of our ability to test the theory. What I love about moments like this is the ridiculous extreme things these scientists did, these 200 scientists, in pursuit of a goal that seemed impossible, and yet they achieved it. I want to extend my personal congratulations to everyone on the team for an amazing discovery. I'll be linking to all their work in the description.
We have gone straight to the edge of the event horizon and seen the point of no return. For the past 2 decades, a global collaboration of scientists around the Earth have been putting together an Earth-sized telescope with a single purpose: to image a black hole. And now we have done so.
Right, we have done something extraordinary. We've made the first picture of a black hole. If you want to make a test of the fundamental theories of the universe, you want to go to the most extreme laboratories in the universe. And a black hole is that.
This is an extraordinary moment in science. It's the best verification that we have that black holes aren't just theoretical scribblings on a blackboard, musings of theoretical physicists, but real entities roaming the universe.
We all understand from a mathematical point of view that black holes exist, but to actually see something is a very visceral experience, and I think important for science and also for us to believe in it.
The black hole that we've imaged is M87. This is a behemoth. It's a black hole that's 6.5 billion times as massive as our sun. And it sits in the center of a galaxy 100 times larger than our Milky Way, which itself lives at the center of a cluster of thousands of galaxies, Virgo. They are quite literally gravity run amok, a key window into one of the least understood and yet most omnipresent forces that we are all faced with: gravity. This provides the first time that we're able to study in detail the stage that gravity sets for astronomical phenomena.
I think we've been extremely lucky. I'd expected that we have to work for years and years, do many observations until we get a final image. And then we look at our first source and we see that ring. We see the event horizon and we see that shadow, that dark region. And you know immediately we're looking at an event horizon and a black hole from all sides at once in this thing. We see at a region where time stops. This is a very different part of the universe that we're seeing for the very first time.
The most striking feature in these images is the footprint of gravity. This ring-like feature with a central dark depression, the shadow of the black hole. That region where the photons that we see would have had to have come from below the horizon and are therefore absent.
It's amazing to be able to work on data which have never been obtained before. To have highest resolution observations, this is a unique time for a scientist in his or her life to work on these kind of data. So to see into an area where we didn't have any information before.
This first image doesn't represent the end of an endeavor, but rather the beginning of an era in which we have a new key window onto how gravity behaves and how it shapes our universe.
The future of this project is amazing. Now we want to make the first movie. Now we want to understand how space-time rotates around the black hole. We'll do that by putting more telescopes around the world to make our virtual lens even better.
It signals the beginning of this new era in which we can study the life and times of these extraordinary objects in a way that was simply impossible before.
One of the most uplifting things for me is the team that we've built and the fact that we're doing something that people have told us was impossible. And when you, at the end of the day, do something that people tell you you can't do, it's an incredible feeling. And I think the whole team is very, very proud that we've accomplished something like this. It's not just for us, it's for everyone.